So sigma is a tensor. It has the components, and we'll typically write them like sigma 1, 1, sigma 1, 2. And that's the way I typically always use x1, x2, x3, but I know it's very common and probably in your undergraduate class that you'd use x, y, and z. So we can also write this as sigma xx, sigma xy, sigma xz, sigma yx, sigma yy. Where I just say 1 is x, 2 is y, 3 is z. And so if we go back to our little cube, if we have a traction on, say this is x2, x1. So if we have a traction on this surface, then its components in terms of this guy are going to be sigma 2, 1, sigma 2, 2, sigma 2, 3. All right? And the reason it's 2, 1, 2, 2, 2, 3 is because this face is defined by the normal vector in 2. Right? In 2, in x2 direction. So whenever you see this, I mean, that's how you come up with this. The first indice is the face, right? Is the face defined by the normal vector, and the second indice is the component number. Right. So likewise, if I also label these axes x, y, z, and then we looked at what this traction is, what would it be? Now this would be now not in 3. In terms of x, y, and z, this would be in z, right? So this would have components zx, zy, zz. This traction vector. Okay? So that's the sort of geometric definition of stress. It's the tensor that, when multiplied by a normal vector to a surface, gives you the traction vector acting on that surface. If you go here, yeah, it would, you're going to have another vector acting this way, right? So the traction vector, would be like the negative. The stress would be the same, and you'd have a negative, yeah. So it'd be the same, right? Because the unit vector would be negative, so you can just multiply this equation by -1, and you get the same thing.